All right. So let's start with the concept of refraction of waves. Now, before we go into the refraction of waves, please let me do a recap to tell you that waves have the following properties. Waves have these following properties. So as you are learning about refraction, I want you to observe these following properties. Property number one, waves have direction of propagation. This implies the direction in which the wave moves, direction in which the energy flows. That's one. Then you have waves at what we call speed, waves at what we call frequency, waves at what we call wavelength, and waves at frequency, it also have period. These two are always tied together. These are some of the properties of the waves, okay, which characterizes a wave, which identifies one wave from another wave, okay. Now, what is reflection? All waves undergo reflection. Reflection, in a very simple sense, in a general sense, means a wave approaches a certain surface and then it hits the surface and gets bounced off. Basically, that is what reflection is all about. Of course, this is not the detailed understanding because there's so much details we got to learn after that. But overall understanding, the overview will be basically a wave approaches a certain surface, let's say this surface, it hits the surface and then it bounces off. That is reflection. So what we want to see is, all right, what happens when the waves undergo reflection? Does the direction of propagation change? Does the speed change? Does the frequency change? Does the period change? Does the wavelength change? All that we need to verify. So, but before that, we got to first understand how reflection occurs, okay? So let us take a simple general case of refraction. So let's say this is the refractive surface, okay? Refractive surface, okay? Refractive surface. Now, what wave are we talking about? Are we talking about water waves? We have three types of wave to consider. Are we talking about water waves? Are we talking about sound waves? Are we talking about light waves? Now, water waves, sound waves, light waves, they are different. They're not the same. As a result of that, the reflective surface, because of the different nature of the waves, can be different. Now, in the case of light, the reflective wave that is favored for reflection to occur is a smooth surface, such as a mirror surface. But in the case of water waves and sound waves, reflective surface has to be hard surface. So let me take water waves. So I'm going to take as a water wave as the incident wave. Incident, remember, that's a terminology. The wave that approaches is called the incident wave. And I'm going to incline that to a certain angle like this, like that. This is my water waves. All right. Now, I draw about three. Hold on. Let me just get that right. This is freehand drawing, example draw. Okay. Now tell me, what do we call these lines? What do we call these lines? What does these lines represent? For a wave, when you draw a diagram like that, what does this line represent? It represents wave front. It represents positions of many crests, which are all in phase, PHASE. So that's one wave front, that's another wave front, that's another wave front. These wave front are straight wave fronts. Therefore, what you're looking at is a plane wave. So this is a plane wave front of plane waves. And what do you call the spacing between two wave fronts? So spacing between two wave fronts is the same as the space between one crest and the consecutive crest. Therefore, it will be lambda. So that's your lambda. Okay? So now, this is what we call an incident wave. So this is an incident wave. I'm going to label it as incident wave. All right? Now, we are going to draw the diagram that shows the reflection of these water waves. Okay, just like for light, we have ray diagrams. This diagram is for water waves. So in order for you to draw the diagram of the water wave to indicate upon hitting the reflective waves, it undergoes reflection, you have to have a reference line. And that reference line will be the direction of propagation. So we use the direction of propagation as our reference to show the phenomenon of reflection. We're going to use the direction of propagation. So where is the direction of propagation? Where is the direction of propagation? Recall what I taught you in the previous lesson. Where is the direction of propagation for these waves? Anybody can tell me. Where's the direction of propagation? Remember, direction of propagation is always perpendicular to the wavefront. Very good. It's always perpendicular to the wavefront. So you could draw a line like that. If I draw a line like that, you can see that line is perpendicular to the wavefront. So there is an accepted direction of propagation. You can take the direction of propagation here as well. That is 90 degrees. So that's accepted. But normally, all right, to standardize, we take the middle. So we take the middle to indicate. Actually, you can draw anywhere because the direction of propagation, as long as it's perpendicular, it is direction of propagation. So I'm going to draw a line right at the center like that. So all the way down like that until it reaches the surface. And to show it's a direction of propagation, I put as a perpendicular sign like that. And all direction of propagation must be indicated with an arrow to show its direction. So it hits the reflective surface. Now at the reflective surface, where the direction of propagation meets the reflective surface, you have to draw an imaginary normal. Normal is an imaginary line that has to be drawn to validate what we call the angle of incidence, the angle of reflection, and hence allows us to draw the reflective direction of propagation. So I have to have the normal. That's my normal. Okay, and that's 90 degrees. So when you put 90 degrees, you don't need to draw. See, normal is indicated letter A. You don't need to do this if you put a 90 degrees. That 90 degrees automatically tells you that's a normal. And that's my angle of incidence, which I put a theta and I put an I there. Okay, now, always will follow and obey the law of reflection. Okay, so there is a law of reflection which states that the angle of incidence will be equal to angle of reflection. So reflection obeys the law of reflection, which states that the angle of incidence will equal to the angle of reflection. So that's the angle of incidence. So, and remember, angle of incidence is the angle from the incidence ray to the normal. So angle of incidence. Angle of incidence is the angle between incidence ray, follow the concept, and normal. That means if you want to find the angle of incidence, detect, identify the incident ray and the normal. So in this case, it's a wave, not a light ray. So I put incident wave. So the angle between the incident wave and the normal. So that's your incident wave. That's your normal. And see, you need to have a reference. So I'm using the direction of propagation as my reference. Now, what happens if you were to draw your direction of propagation here? You will get the same thing, because if you draw the direction of propagation here, your normal will be here and they are parallel. So the angle will still be the same. So it doesn't matter where you draw the direction of propagation, but it's good to draw at the center. So now, roughly, you don't need to be so particular. Okay, so you draw roughly, measure the same angle. So to show the examiner the angle is the same, you're following the law of reflection. Use the mathematics concept, do that. Now the examiner knows the angle is the same. Okay, and draw. This is direction of propagation of the reflective wave. Direction of propagation of the reflective wave. You have drawn. Okay, that one. Okay, all right. And now you got to draw the wave front of the reflective wave. Remember, it has to be 90 degrees. So that wave front 90 degrees. All right, so I'm going to draw the first one. That's my wave front. Okay, so remember, you will be asked to draw, so you got to draw. So wavefront 90 degrees line. Okay. So to indicate 90 degrees, just put a 90 degrees. Now, how many wavefronts must you draw? There are 3 wavefronts here. Draw 3. This is where you got to ask yourself, the next wavefront I draw, what should the spacing be? Because the spacing has a meaning. It means lambda, wavelength. So when refraction occurs, does the wavelength change? Remember, I told you to look at that. Remember, the wavelength does not change. No change on the wavelength. No change on the frequency. No change on the period. And no change on the speed. So all these will not change. But you can see the direction of propagation. This one changes. For the incident ray, that's the direction of propagation. For the refractive wave, incident wave, for the incident wave, that's the direction of propagation. For the reflective wave, that's the direction of propagation. Of course, they are not the same. So direction of propagation changes. Lambda must be the same, so roughly the same distance. Roughly the same distance in actual exam. Please measure the distance. I'm using a freehand sketching. All right, roughly like that. Roughly like that. Okay, that's my lambda. So this one a little bit off. Okay. Okay, that's a lambda. So here to here, it's lambda. So lambda incident and lambda refractive is the same. Okay, and this one will be theta. This is how you draw the diagram of refraction of a water wave, which is plain water wave. Okay, all right. Now I want to ask you a question. Think and answer. During reflection, does the velocity change? And give me one reason. State your reason. During reflection, does the velocity of the wave change? What's your answer to that? What's your answer to that? I repeat, during reflection, does the velocity of the wave change? State your reason. Now, remember the biggest difference between velocity, one of the biggest difference between velocity and speed is the direction. All right, it's the direction. I already told you here, the speed does not change. That means the speed of this wave and the speed of this wave does not change. What does that mean? The magnitude of the speed, magnitude does not change. If this is 20 meters per second, this is also 20 meters per second. The magnitude does not change. But when you say velocity, you are now talking about a vector quantity. So when you talk about vector quantity, the direction becomes effective. The direction is important. So 20 meters per second in this direction and 20 meters per second in that direction is no longer the same. And now the velocity changes. So during reflection, speed does not change, but velocity changes because the direction of propagation changes. That's your answer to that. I have another question. Does the amplitude of the wave change? Does the amplitude of the wave change? What's the answer to that question? Think again what I explained to you. Always remember, do not simply say yes or no without a reason. Think. I asked you, does the amplitude change? So you got to ask this following question. Okay, you got to ask this following question. Amplitude of a wave represents what? First ask that question. Amplitude of the wave represents what? Give me the answer to that. Amplitude of the wave. Now, amplitude of the wave represents energy. Amplitude of the wave is the maximum displacement of a particle that is oscillating, all right, measured from its equilibrium point. That is true, but that's the definition. My question is what? My question is not what is amplitude. My question is, what does amplitude of a wave represent? Okay, so it should be energy. All right, amplitude of the wave represents energy. Bigger the energy of the wave, bigger is the amplitude. Now, as the wave propagates through the medium. All right, this is water wave, so it's propagating through the medium of water. What is happening to the energy of the wave? The energy of the wave is dissipated, not lost, dissipated, meaning transferred to the medium. So as the energy of the wave is transferred to the medium, the energy content of the wave will start decreasing, decreasing, decreasing. So when it hits and then it moves this way, it is again dissipating energy. It's again moving to the medium, which means it is transferring its energy to the medium. So in any phenomenon, no matter diffraction later you will learn, interference that you learn, energy of the wave will always be dissipated to the medium, causing its amplitude to decrease. Okay, it will cause its amplitude to decrease if the wavelength is maintained the same. If the wavelength is maintained the same. All right. So if the wavelength is the same, then amplitude, yes, will decrease because energy is dissipated from the wave. So that should the answer be. So in terms of amplitude, the amplitude decreases due to dissipation of energy.